Welcome back to learnpiezo.org, and today we're going to be answering a question of a person who recently contacted me about a specific piezoelectric application and different problems he was having. So first, I'll outline the application. And this application is specific toward measurement of density. So density is kilograms per meter cubed. And this is density in a liquid. So if you have a pipe, and I can draw that out here, and this pipe contains some liquid, which is discolored. Let's say it's a blue liquid. And if you have a piezo, and I'm going to draw this piezo as gray. If you stick a piezo on this side, and you stick one on this side, this is a pipe now, and it has a circular circumference, and then you excite vibrations from one side to the other, so we send vibrations across using a voltage. The time it takes for the wave to propagate can be used to determine the density of this liquid. So this is the application, using, applying electric field here, namely like a pulse, and then seeing this waveform appear and noticing the spike here, and the time of flight, they call it, is the resulting. So here we have the transmitting piezo, and here we have the receiving piezo, T and R. There were several complaints which the respected engineer had. The first complaint was about his piezoelectric materials. He said that many of them had varying properties. And actually he came asking me, can you tell me a piezoelectric provider that doesn't have all these varying properties in my materials? I said, okay, there are different material providers, but it usually doesn't vary that much between the different piezoelectric materials. They're produced in a pretty standard way by the same company, especially if you have the same batch of materials. So upon further inspection, he was describing what we know as the resonance frequency. And he was saying, and for this application, he had discs, and he's talking about the resonance in the 3-3 direction. So the poling directions like this, and the resonance vibration, it's in the 3D direction. So longitudinally, that's the vibration. Not longitudinally, in the thickness. So he was saying that, and he used my videos about how to measure the resonance frequency. Basically, you have your piezoelectric crystal, and you have a resistor. Okay, and you have your ground, and you have your oscillating power supply, which also should be connected to ground, and you measure the voltage here across this resistor, which we can make it, let's say, 1 ohm, and you measure the point of highest current. So at a certain frequency, if you plot frequency here, and you plot current here, or you can say voltage 1, but voltage 1 equals V equals IR, right? Voltage 1 equals the current times the resistor. So if you divide, the voltage by this resistance, which is 1, you're going to get the current. So basically, it's the current here. So at a certain frequency called omega R, you're going to get the largest, amplitude. Let's call this RMS value of the current. So you're going to get the largest amplitude of current. This is the resonance frequency. And he was complaining to me that the resonance frequencies for this material, the material that he ordered, was varying significantly. Some were 4 megahertz, and for the thickness mode, assuming this is probably like 1 millimeter or something like that, you're going to get in the megahertz. This is going to be the resonance frequency of choice. You're also going to get a lower resonance, which is going to be in the kilohertz region, which is going to be greater than 100 kilohertz. So usually greater than 100. But that is the longitudinal vibration. So if you had vibration around the radius, so it'd be sort of extending in each direction. So if you had your disc, each direction, we're looking at the disc from the top, the vibration would be like this. would be radial, versus vibration here where we have vibration in the thickness. So we're looking at the top. So the vibration was sometimes 4 megahertz, 5 megahertz. Like there's so much variation. So he said that, can you direct me toward a company that can provide me similar results? So there are many answers which I gave him. Firstly, directly answering the question, how can I understand? How can I make sure that the material properties that I measured are the same? And if you saw in the last question that I answered on this website, you can use the LCR meter or whatever way you can to get the capacitance of each material and the loss tangent. And those loss tangents, you can use this to measure the permittivity. And basically, if you compare the permittivity and the loss tangent of each of these materials, then you'll be able to understand are these materials the same or not. It doesn't. Do you see the permittivity and the loss tangent depends on the piezoelectric and the elastic properties and the dielectric properties of the material. So because these parameters all relate to each other, just measuring these two and comparing them between two different samples of the same composition, the same batch, you can tell which one is similar. And there is actually I found that there is some dissimilarity in batches. So that's something you may want to consider before starting an experiment, depending on how similar you want your results. It may be worth picking and choosing which material you're using based on their permittivity and tangent delta, prime to be exact, but whatever. So this is the way to determine whether your material properties are the same. However, he had huge differences, 4 and 5. Let's show 20% difference, let's say, in elastic compliance. And the elastic compliance governing the thickness direction would be elastic compliance 11E. But anyways, that's something else. It would actually be 11D. It'd be S33D. Okay, there you go. So there was no way there was 20% difference in the material properties. So basically, I found out that he had varying thicknesses. He had 1 millimeter thickness, 1.2 millimeter thickness. And this would cause at least a 20% difference in the resonance frequency approximately. So immediately I said that, look, you have to get the materials with the same thickness. That's the first step. To get the same resonance frequency, you need to use, same resonance frequency, you need to use the same thickness. Okay? That's important. So next, this is the first problem. He needed a little bit of help understanding how resonance frequencies were related. The next problem was a little more technical. I was able to solve it though. He said that I don't get a very nice signal. So let's draw a little graph here. And we're going to draw different axes for different signals. We'll just draw 3. I think I may only need 2 for transmitted. So this top part is going to be the transmitted, and this bottom one is going to be the received. So we transmit this voltage signal. Let's call it a voltage pulse of this duration. And then later, at a later time, we're going to, and let's call that delta t for lack of a better. Another time we're going to receive this pulse at this side, on the receiving side. And basically delta t, also known as a time of flight of the wave, is the time it takes to get to one side of this pipe to the other one. So this delta t looks like that. However, he didn't have such a nice response. That's the problem. Basically, the response was like this. There was, after this was the applied voltage, but actually he ended up getting some type of ripple effect here. And also, when we got our signal, there was sort of like a ripple effect here, and the signal was very lousy. This was a signal received. This was a signal transmitted, which is a nice square wave. We directly in the material, we applied a square wave, but when we measured the voltage, we got some type of rippling effect going on. And when we received the voltage, sometimes it was very irregular what the voltage was. It was really small, it was really high, really low, bouncing up and down. So this was a problem. So how do you solve this problem? There are a few issues with this. I'll outline the issues. the first issue, or probably the main one, or probably the only one, the first issue is that you need to apply multiple pulses. Because you want large vibration. Multiple pulses results in large vibration due to resonance. You know, if you applied a resonance frequency, I'm going to draw two things here. Let's assume this top part was voltage and this bottom part was vibration. And let's say we apply a voltage equal to voltage naught sinusoidal at the resonance frequency, and this is time. If you apply it at the resonance frequency, like let's say we applied a constant voltage, let's just consider this. We're going to be building up our vibration. Our vibration is going to be increasing small, getting larger, getting larger, getting larger. So this is going to happen. There is an amplification which occurs if you use multiple pulses. Okay. The second problem which happened was that the resonance frequency, the second problem here, was the resonance frequency was not considered. The resonance frequency was not considered. So if you remember back here, where I talked about these rippling effects. Why do these rippling effects occur? Because there's transient vibration. As soon as you stop it, this right here is going to be rippling according to the resonance frequency. Okay, so if you want to decrease ripple and therefore increase the measurement integrity, you drive at the resonance frequency. So I think he was using something like microsecond pulses. Let me use a nicer color there. He was using something like microsecond pulses. His pulse was microsecond. However, if the resonance frequency was 1 megahertz, is equal to 1 e to the 9, 1 divided by 1 e to the 9. You have to use that resonance frequency, which would be in the nanoseconds. You have to apply a nanosecond type of pulse, or 0.1 nanoseconds, in order to properly, 1 over this is e to the minus 9, 1 over 10, so it's 0.1 nanoseconds. You have to apply nanoseconds. So therefore you got this rippling effect. So if you apply multiple pulses, and at nanoseconds results, you're going to get larger vibration, and you're going to get a cleaner signal. So this was the second part. The resonance was not considered. Multiple pulses were not considered to get a larger vibration. But both of these sort of go hand in hand. The next question which was given was that, okay, so another consideration to get reasonable and repeatable results was the practical experimental assembly, you could say. Okay, so what do I mean by that? So you have to bond the piezoelectric material to the pipe. And in the bonding process, there can be many errors or many different deviations and changes in the way you do it, just based on human error. So there's basically human variables, or if you have human variables, or just variables of processing. You can never make, no two things in the world are the same. You make the exact same product one after the other. There are going to be some slight changes in their dimensions. Maybe you can't notice them. Maybe you can't even measure them, but they're there for sure, because no two things in the world are alike. I mean, alike in the sense that they're exactly the same, So there's some variation which even occurs. So there's some human variables which can also occur if you're bonding everything by hand. So how can I tell what these human variables are, and how can I control this bonding process and understand if I'm bonding things correctly or not? So when you bond a piezoelectric, so we have this disc, And now we want to, let's say, bond it to this substrate here. After we have bonded it, and then you apply electric field. So here, if this was metal, you can just attach one here, and assuming that some point of this is not bonded, therefore the metal actually touches the electrode, you may have to like pull out some type of thin electrode from the very edge if you have either a non-metallic surface you bonded to, or if your bonding layer is thick. But if your bonding layer is really, really thin, there's probably some portion of the metal sheet which is touching your bottom electrode of your piezo, because piezos have electrodes on top and bottom. They have to be electrically activated, and the losses which will occur through, if there's actually epoxy here, there will be a reduction in the electric field across the PZT because of the drop in voltage over the epoxy, which is acting like a dielectric material of low dielectric constant, which will drop most of the voltage actually. So be careful about that. Pull out a sort of shim or something like that to get that electrical contact in, and make sure it's flat. So okay, what I was saying here. So you have this contact, and it's when you vibrate the piezoelectric, it's going to be constrained, or it's going to be semi-clamped. Obviously, it's not completely clamped because you can generate vibration. Semi-clamped. And what happens when you semi-clamp a material, if I can draw for you the equivalent, the DC, and this also somewhat applies to AC too, the DC equivalent circuit, essentially what happens to the capacitance. So this is the part related to the clamped. So if you completely clamp the material, you're not going to, and this is the part related to the deformation. So this is the deformation related to capacitance. And in total, what you're actually measuring in practice is a single capacitor, which is related to the dielectric permittivity and constant stress. This is completely clamped. This has the motional part. So we can understand these two. But basically, what happens is you diminish the effect of this, because the effective compliance of the material gets larger as you are increasing the external material. And because the constraint gets larger, the material effectively feels stiffer and it's more constrained. Therefore, this contribution will decrease. It's not completely clamped, but it's almost clamped. So the contribution of it will decrease. Therefore, the capacitance, the effective capacitance, will decrease. So if you said this clamped this is greater than completely unclamped, or this is semi-clamped because it's free stress, but we sort of clamped it on the bottom. This is completely clamped theoretically. It's a little bit different than that. So this is a practical clamping. There's still vibration which occurs, but it's sort of going to drag this. It's sort of, the vibrations are going to sort of go in all directions, which sort of makes the material feel like it's stiffer. So this clamping reduces the capacitance. So the way we can tell, how can we, the question is, how can we tell if we bonded the PZT in a repeatable fashion? So you can before, I'm going to draw two sections, before and after. So if you have before and after. So if you have a capacitance CO, or let's just call it C1, and afterwards we have a capacitance 0.6 C1. If we compare this ratio, capacitance drop 40%, right? If you compare this ratio before and after for each of the ceramics that we bond, we can understand that we have clamped each one in a similar fashion. And anyway, you should first identify those piezoelectric components which have the same capacitance, And then what you should do is you should see how much do they change when I bond them. And if they're all changing the same amount, you can be sure, in all likelihood, that each of them are bonded in very similar ways, and therefore you should have a repeatable result between them. So let's just repeat our discussion. We first introduced the application, which was determining the density with time of flight, and you can look at that up, how a wave travels through liquid and how that can be used to determine the density. Next, we can look at how do we measure the resonance frequency, and we complain about varying properties. So I said that, hey, you can use the LCR meter, you can measure the capacitance, which can give you the permittivity, and you can measure the dielectric loss, which can tell you, because due to coupling of properties in piezoelectric materials, determination of this material property and this loss property can give you pretty much all the information you need in order to look if two materials from the same batch of materials are the same. But actually what happened in this case was the thickness of the materials were different, therefore the resonance frequencies were different. Here I described the pulse, and the things for concern was that there was a bad receiving signal, and the transmitting signal sort of had a ripple in it. And next, I said that using multiple pulses, we can induce a larger vibration. If you induce a larger vibration, basically what this would look like if you had several pulses, assuming that, let's say, the resulting pulse would be here, it's drawn in red, you'd get sort of like a wave packet, a nice like wave packet, like type of thing. So you get larger vibration, and you would also get this like nice waveform which occurring. And these pulses should be applied at the resonance frequency. If you want to apply more than one pulse, applying one pulse at the resonance frequency will provide a nice clean signal. But multiple pulses is better for a higher voltage signal received on the receiving piezo. Okay, multiple pulses, resonance frequency, you must consider that, but by your thickness, you can measure your resonance frequency using the maximum current, which I outlined here. It should be around the megahertz frequencies for the resonance frequency measured. So you have to know sort of beforehand which resonance frequency you're searching for. And for this application, you should use a disc. Square piezos have different resonance frequency modes, so if you're using a thickness type of resonance, a disc is the best bet, although the square can be used, but there's a lot more complications. A disc is much simpler and better. Experimental assembly, if you clamp a piezo or if you bond it, the capacitance is going to reduce, and it's going to reduce due to the decrease of the motional contribution to our capacitance from the deformation, because the material it'll feel stiffer when you apply an electric field. It won't deform as much. So how can we tell if the bonded PZT is bonded in a repeatable manner? We basically see the capacitance before and after, and we test that for different piezoelectric materials which have a similar capacitance before and after, and by comparing that, we can tell that yes, the bonding is the same, because the only thing changing the capacitance in this case is the bonding. What you can also tell would be very, very cool if you also looked at the dielectric loss, because now that you bonded it, it's bonded through epoxy, which has much larger losses than piezoelectric materials themselves. Because if you look at the tangent delta and the effective new permittivity, from the clamping, you can really get a really good idea about how you bonded it. So this is determine the loss properties, this determines the real properties. This number will go up after clamping, this number will go down after clamping. Thanks for watching. I look forward to seeing you next time, and anyone who has any questions, I'll do my best to make up an answer that sounds reasonable. Thank you.